I'm very delighted to welcome Dr. Stephan Munch, professor in applied mathematics and ecology and evolution behavior at the University of California, Santa Cruz. Dr. Munch's research focusing on dynamics of multi-species system and the feedback between species interaction, large-scale meta-analysis, statistical method development, and ecology theory to address problems ranging from fishery-induced evolution and transgenerational thermoplasty to parasite community ecology and storm surge prediction. Currently, he is dedicated to building robust ecosystem management framework that remain effective even when system cannot be fully specified practical necessary for the real-world conservation and resource management. His work continued to bridge fundamental ecology theory with actionable solution for fisher, climate reliance, and biological conservation. So let's welcome today's speaker.
Thank you. That's a very, very nice introduction. Thanks a lot. So I think you guys can see my screen, but I can't at the moment.
Yeah.
So I'm gonna turn me off
Yeah,
and put
please.
you guys away, and then so I can look at what I'm actually
Sure,
doing. So
sure.
all right, me off, you away. Hopefully I can see my screen. Where is it? You know, you'd think after 5 years of doing Zoom.
So you are in slide 3.
Oh boy.
Okay, we can see it.
I can't see my slides at all.
Oh,
Sorry, this
maybe
is not.
you're going to maybe close the PPT and then open one more time.
Yeah, that's a good idea.
Yeah.
All right. So, do you guys see my screen now?
Yes.
Okay, super duper. All right.
Good.
So,
Perfect.
all right, great. So thank you, Professor Jay, for inviting me to speak today. That's really a treat for me. And I should start out by saying that, you know, although I have a
Ah.
professor position in applied math, I'm an
Mhm,
ecologist by training,
mhm.
not a mathematician. So yeah, so I will talk about things like species, populations,
Uh-huh.
abundance, and I hope that you
Ah,
guys can
by the
imagine.
way, Stephen, can you turn on your video if possible?
Uh, I would rather not be distracted
Oh,
by
okay.
me, if
Okay,
you don't
gotcha,
mind.
gotcha. Okay,
I'll
gotcha,
turn it
gotcha.
back on when there are questions, though.
Okay, gotcha. Okay.
Thank you. Um, so, um, yeah, so I use nonlinear dynamics as a lens to try and understand complex systems, and today I'm going to focus on what I think we can learn about stability and bifurcations from time series data. And you know, this is just in case you didn't want to see anything about fish. Here's a COVID.
Mhm.
All right. Okay. So biological systems are inherently complex, but when we try to write down specific models for them, for very practical reasons, we focus on small components of the system, implicitly dividing the world into two classes of state variables, the observables. Those are X throughout the talk. Those are the things that we care about. And then the unobserved variables, Y, which is literally everything else. And we usually model just the observables, which is reasonable when we have strong timescale separation. But when that's not the case, we probably need to do something else. And when the unobserved variables interact with the observables, it's very common that we end up with memory effects. As an illustration here, consider a linear approximation of this general setup, where the matrices F and G describe interactions within and between groups of state variables, and that's summarized in this little diagram off to the right. To see how memory arises, well, we could solve the lower equation for the Y subsystem and then plug that answer back into the dynamics for the observables. And when we do that, the result is a bit of a mess, but it's exactly what we'd get working through the loops in the system diagram here. So we have this direct, the Markovian component, which is X feeding back into X. And then we have, you know, this memory component, which is X going to Y and then back to X, or going to Y and then staying in Y before going back to X, et cetera. And so we have this sum, which represents all of these indirect paths from X back to
Mhm,
itself through Y.
mhm,
The Importantly, this has exactly the form of a linear autoregressive model, which provides a strong justification for these, which are widely used in many disciplines.
Mm,
Now, I did this approximation using for a linear system. So, but the Mori-Zwanzig formalism from statistical mechanics shows that this sort of thing is true in general. And the upshot is that we should expect memory effects whenever the observables, the things that we're modeling, interact with the things that we aren't measuring. So to account for unobserved variables when the system is nonlinear, we typically appeal to Takens' theorem of delay embedding, which says that when we have an n-dimensional system that converges to an attractor whose dimension is d, and we have some scalar observable that's a function of the system, say we'll call that h, then generically the delay coordinate vectors of h, so that's h now, h last time, h some number of steps ago, thinking about that as a point in a space, then generically the delay coordinate vectors are a one-to-one and invertible transformation of the attractor for that system, provided that we had enough lags in the vector. And that is, the embedding dimension needs to be greater than twice the dimension of the attractor for this to work, at least generically. To make this a bit more intuitive, here's a short video. This is a three-variable system. We'll call the species here X, Y, and Z. And so in the middle, the time series for each species is being traced out in that center panel. Now on the right, in black, we have the phase portrait, and we're seeing that the same time series and plotted in the phase space are actually tracing out a fairly simple attractor. So these complex dynamics actually are a simple geometric object in the phase space. The thing in red is a reconstruction of the attractor where the x-axes are not x, y, and z, but they're x now, x a step into the future, and x 3 steps into the future. And although the attractors aren't identical, they do share a one-to-one correspondence.
mm,
So what could we do with this? Well, let's say that we don't know the equations, but we do have enough data to make this plot. We know that the system is, and let's say that we know the system is somewhere in here. Well, a very reasonable thing to do would be to ask what happened the last few times the system passed through this circle and use that to make a prediction. And if we repeated that exercise, moving the circle throughout the phase space, we'd effectively be constructing a discrete time model for the system directly from data. And of course, we can do the same sort of thing with the attractor in red. And when we do, we end up with a model in delay coordinates whose dynamics are equivalent to the dynamics in the original state space. And that's what we get from this one-to-one correspondence between the attractors. So, but to operationalize this idea, we're going to need some data-driven way to estimate the delay embedding map. Now, many different methods have been used. Lots of different function approximation tools can be made to work here. And despite what the AI people claim, there is no single best tool. It depends a lot on the data available and the question that we're trying to address. And also, this whole idea of delay embedding has gone by many names in the literature in the past, things like nonlinear forecasting, delay embedding, attractor reconstruction. And in ecology, this has recently been rebranded as empirical dynamic modeling. So throughout the talk, I'll just refer to this as EDM. All right, so for most of the results that I'm going to show, we used Gaussian process regression to do the approximation of the delay embedding map. The reason we do that is because it's relatively easy to control the smoothness of the function that we're approximating. It requires a lot less data than a neural network, and it doesn't require a library of basis functions like something like Cindy does. So for prediction, we use the posterior mean, which is determined by a combination of the data and the covariance function, and that's shown here. So for the covariance function, we're using a squared exponential covariance in which each input gets its own inverse length scale parameter. That's these phi i's. Of course, you could do something more complicated, pick a different covariance function, but this is a good off-the-shelf thing that works in a wide range of settings. Importantly, with this parameterization, when we set the length scale parameter, inverse length scale parameter to 0, the ith input, the corresponding input drops out of the model. And so setting a prior on this with a mode at 0 encourages sparsity and avoids overfitting. And that's going to be illustrated here. So if we don't apply the prior, we fit this GP to the white dots in that graph, the surface that we end up with is that rainbow thing, which is kind of complicated. But when we do apply the prior, what happens is the irrelevant input just drops out of the model. And in the machine learning literature, this is referred to as automatic relevance detection, which is nice when it works. All right, so let's apply this setup to some real time series, and I'm going to show you some
Oh,
results based off.
Stefan, so
Yeah,
before for that Gaussian process part,
yeah,
is there any some the delay embedding components are incorporated here? The
yes. So
which part is a time
I'm sorry
delay?
that the
Yeah,
notation on this is not
yeah.
clear. So x, the vector x here is the delay embedding
Ah,
vector,
okay, so
and
I
y
see.
is the
So
next state, the state that we're trying to predict.
so here X observation incorporate the past information.
Yes.
Okay, got it.
Sorry, I just grabbed a generic GP slide here.
No, 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 no problem, no
Sorry.
problem. Yeah, thank you, thank you.
Sure. All right. So we compiled a database of 427 abundance time series representing birds, mammals, fish, insects, zooplankton, and phytoplankton. And going out on a limb, I might say that this was a global meta-analysis, but really most of the time series are from Europe and North America. And for each time series, we fit a linear autoregressive model and our EDM model and use those to make leave one out forecasts. And to facilitate comparison across time series with widely different measurement units, we computed the mean square error in our leave one out forecasts divided by the total variance. So we end up with a dimensionless quantity. And one minus this is I'll refer to as the prediction accuracy or prediction R squared. And in other fields, this is referred to as the Nash-Sutcliffe efficiency. But, you know, the important part is one is good, zero is
Mm.
bad.
Mm-hmm.
All right. So before I show you the results, I want to give you a sense of what the time series data actually look like in this database. The
Oh,
top plot shows some counts of the great crested flycatcher, which is a bird.
uh-huh.
And the bottom shows cell densities of cyanobacteria in Lake Zurich. Those are not a bird. But the time series vary quite a lot, both in terms of their scale and and the number of observations that we have.
So cyanobacteria fluctuation is more faster time scale compared to the bird. Can we?
Much faster,
Yeah, okay,
yes. So
much
the
faster. Okay.
Yeah, the cyanobacteria turnover on the scale of days, and the birds live,
Mm-hmm.
many years.
Got it, got it.
So, no. All right. So here is how the linear model versus EDM comparison turns
Mm-hmm.
out. The horizontal axis is the prediction accuracy for the linear model. The vertical axis is prediction accuracy
Oh.
for EDM. And the points are color-coded by taxa. So the prediction accuracy for the EDM and autoregressive models are strongly correlated, and they nearly run the full range from 0 to 1. But the main thing to take from this is that the EDM model is at least as good as the autoregressive model and sometimes a lot better,
Mm.
particularly when the autoregressive model doesn't do so well. So down here, we get
Mm.
much bigger improvements in prediction. So
Uh,
now we
Stephen,
expect.
I'm really sorry. So here,
No,
what we
that's okay.
predict is a future of the each species based on its history. Can we understand
Exactly.
that? Okay, so we don't use other species info, only its
Just
own.
one species at a time,
Okay,
one time series at a time.
and
Yeah.
then okay, got it.
Oh,
Oh,
thank you for
this is a
asking.
very this very cool figure.
Oh, thank you.
Yeah, yeah. Wow.
Now, we expect linear models to do well for
Mm-hmm.
stable or oscillatory systems, right? So to try and understand when the EDM model is really outperforming the linear model, our next question turns to stability. Now, the standard tool for quantifying stability or chaos is the Lyapunov exponent, which has this impractical limit as time going to infinity. So rather than get into an argument about whether or not we can estimate the real Lyapunov exponent from data, I'm going to propose a quantity which I'll call the practical Lyapunov exponent, which is really the same thing, just evaluated over the length of the time series. So to estimate that, we fit our delay embedding map, we calculate the Jacobian for that, and then take the product over the length of the time series.
Mm-hmm.
And use the log absolute value of the dominant eigenvalue to as our proxy for the Lyapunov exponent. Now, this is probably not the Lyapunov exponent, but it should quantify stability over the length of the observed trajectory. So what do we expect to see if the practical Lyapunov exponent is really telling us something about stability? Well, the vertical axis here is the difference in prediction accuracy between our EDM model, the nonlinear model, and the autoregressive model, the linear model. So on the left, where the dynamics are stable, the only reason populations fluctuate is because of stochasticity, right? So the AR model ought to be just fine. That is, we won't do any better in that case using EDM. On the other hand, when the dynamics are unstable or chaotic, we would need a state-dependent model to account for the nonlinearity. So we expect the difference in performance to be greater. In the middle, where the dynamics are, neutral or possibly cyclic, it's less clear what should happen. So I've left kind of a big gap there. So here is what it looks like for the real data. And the difference in prediction, again, the vertical axis is the difference in prediction accuracy. And on the left, we have small differences when the series are classified as stable. And on the right, we have big differences in the series, bigger differences anyway, when the series are unstable or chaotic. And the upshot is that the Lyapunov exponents that we estimate from data do a nice job of telling us when an autoregressive model will suffice and when something more complicated is needed. So, all right. At this point, I'm going to leave the stability stuff behind and switch to talking about bifurcations and tipping points. As a few of you mentioned at the beginning, complex systems have multiple attractors by stability, and there's a lot of interest in anticipating tipping points or identifying bifurcations. In ecology, we often have multiple attractors, and in ecology, we've observed regime shifts in many systems. Things have switched where we switch from coral reefs to algae-dominated reefs, or kelp forest to urchin barrens, or on the right, where we go from clear lakes with submerged vegetation to green phytoplankton-dominated lakes. I would be keen to hear from you guys if there are critical transitions like this, other critical transitions that might be of interest to study with these tools. When I was thinking about this before for medical applications, all I could come up with was alive and dead, and I was hoping that there were some more reversible transitions to think about. So, since regime shifts can result in major changes to ecosystem services, there's been a lot of effort that went into deriving early warning signals for critical transitions. Most of them are based on the idea of critical slowing down. That is, as we approach a shift, the potential surface flattens out, allowing for an increase in variance, increased autocorrelation, et cetera. And these early warning signals are great because they're generic. That is, they tell us a new regime is coming without having to know the details of the model underlying them. So, can we use EDM to look for critical transitions? Well, one idea is to use the eigenvalues of the delay embedding map to characterize an approaching local bifurcation. And this recent paper by Zach Xi's group in Taiwan shows that the eigenvalue from the delay embedding map does a pretty good job as an early warning signal. So he's applied this to several different systems and calculated the dominant eigenvalue in kind of a rolling window, and the eigenvalue approaches 1 as we get close to the critical transition. But none of these early warning signals tell us about what's coming next. And this is something that if we're trying to manage a system, we really need to know. A lot of the time, interventions to prevent a critical transition are going to be really expensive, and it's important to know what the cost of inaction would be. So it might not be possible to do this in general, but I think that there are some situations where we might be able to make some headway. So here's what I'm thinking. So consider that ball in well picture that I showed earlier, only sort of turned on its side now. The sequence of potential surfaces corresponds to a bifurcation diagram where at low values of some control parameter, so on the left, we have a single stable fixed point at some high abundance. On the right, we have a stable point at some low abundance, and in the middle, we have some region of bistability. Now, if we knew the bifurcation diagram, we wouldn't need an early warning signal, right? We'd already know when the system was going to tip, right? So the question I want to ask is there a way to infer the bifurcation diagram from time series data? Now, in order to do that, we're going to need to know something about the control parameter.
Mm,
And very often we do actually have some idea of what the relevant driver is.
mm,
For instance, in some of those ecological transitions, temperature, rainfall, nutrient loads were the implicated variable. And we can make use of this auxiliary information by extending our delay embedding map to include some proxy for that control parameter. And then given that, we fit our delay embedding maps, and then we can iterate the estimated map over a grid for the control parameter, keeping that fixed, and using that to try and interpolate a bifurcation diagram. To try and make this a little bit clearer, as proof of concept, we started with the logistic map, where the control parameter is the population growth rate, little r here. So you've probably all seen this diagram a million times. So from the bifurcation diagram, we picked 4 values of the population growth rate that are shown by these vertical bars, and we generated time series corresponding to those 4 different values of the population growth rate. We then used those 4 different time series and the corresponding population growth rates to train our GPEDM model, and then interpolate the bifurcation diagram using the fitted model as though it were just a model, and we were using that to construct a bifurcation diagram by varying R. And here's the reconstructed bifurcation diagram. So this is strictly from the data-driven approach with data corresponding to those 4 points in the above diagram. So it's not perfect, but at least in this case, it does a really good job. And it does pick up things like the period doubling cascade and periodic windows, which were not included in the training data. And so I thought that this was pretty encouraging. And so we did it for several other models, including a 3-species competition model that had a period doubling bifurcation, a predator-prey model that has a Niemark-Sacker bifurcation, a single species model that has a fold bifurcation. And for each of these, we use time series of just 1 species, keeping with this idea of doing things always via delay embedding. We collected 50 points for a time series from each of 4 different values of the control parameter for each of these models. And so here's how that turns out. Each panel shows a different model with the vertical bars indicating where we collected the training data. And the blue indicates the true bifurcation diagram. And the magenta is our estimate from our delay embedding map. And the upshot of this is that using a single time series, our EDM approach captures the essential features for the period doubling and hop bifurcations in models of 1 to 3 dimensions. That said, it's not that great for the fold. But I think in fairness to EDM, the training data here is really just a set of fixed points. So there's not a lot of dynamics for our empirical dynamic model to latch onto. And I think that that's why we have trouble here. And the reason I think that is that we can actually do a lot better with the fold if the data we supply it explore a bit more of the state space. We can
Stephan,
get it
I
to...
have a question.
Yeah, go ahead.
In the previous slide.
Yep.
Thank you so much. So these bands indicate the given data sets, right?
Yes, the yellow bars tell us where the time series data were generated.
Does that mean you have only 4 data or many data?
No, we have 200 data points.
I see.
50 from each of those bars.
I see. Thank you so much.
Sure. Thanks for asking. So coming back to this idea that we just really need the model to explore a bit more of the state space, and then we'll do better. We can get it to do that by adding some process noise. So the time series below, instead of just fixed points, we have some oscillations around that. Or we can get there by adding another species And in both cases, the imputed bifurcation diagram, the red, comes a lot closer to the true answer, which is the gray.
Mm.
And so the upshot is that what really matters here is that the data that we use to train the EDM model covers enough of the state space to characterize the shape of the delay embedding map. So with that proof of concept in mind, I want to now use this on some real data. And the test case that I'm going to use is plankton blooms in Lake Zurich. Now, in the 1970s, eutrophication was a big problem. So there are big algae blooms in Lake Zurich, and the government of Switzerland decided to put in a program to try and reduce phosphate inputs in an effort to eliminate those blooms. And it seems to have worked, right? So we don't see those giant spikes in the second half of the time series. And a breakpoint method suggests that a regime shift occurred in fall of 1987. So the question is, can we predict from the first part of the data, say up until 1986, can we predict what nutrient load would induce a shift that eliminates the plankton blooms? So we used monthly estimates of algae abundance, phosphate, and temperature to train the GP, to train our EDM model. And then we treat phosphate as the control parameter, and we just use the temperature to account for seasonality. So when we iterate the model to construct the bifurcation diagram, we're going to drive it with the average monthly temperatures and a fixed value of phosphate, and then repeat that over a grid of phosphate levels to try and figure out what the bifurcation diagram looks like. So we did this using data through fall 1986. That's the blue bar in that graph. The regime shift supposedly occurs around the yellow bar. So we have data stopping a full year before the putative regime shift. And when we use that data to train our EDM model, this is the bifurcation diagram that we get. So importantly, everything to the left of the blue bar here are the phosphate values that we actually saw. To the right are phosphate values that we're extrapolating to. But the upshot is that this suggests that if the phosphate is dropped below about 0.05 milligrams per liter, the blooms should disappear. So the red is our bifurcation diagram estimate. And beyond about 0.05, we just don't see blooms anymore. And so that, it turns out, is more or less what happened. So, of course, this is just one example for one system. And so I would really like to try this on other systems, and I'd be keen to talk about some possibilities if you can think of them. So, all right, for this last piece of my talk, I want to think about something more theoretical. So I think EDM is terrific because we can use it to make useful inferences and predictions without having observations on all of the state variables and without having to know enough to write down equations for the system. On the other hand, EDM sort of implicitly assumes that we don't know anything at all about how a system works other than what we see in the time series. But very often we know a fair bit. And these are the kinds of things that we can include in parametric models, estimates of parameters or specific functions. And it would be really great to be able to build some of that information into our data-driven model. But in order to do that, we need to have an explicit connection between the EDM and the original dynamics of the system. So to clarify this connection, I want to determine what the theoretically optimal delay embedding model would be. So to sort of simplify the notation, we're going to let H represent the history of the observables that we include in our delay embedding model. And when we go to do this in practice, we usually find our delay embedding map by minimizing the mean square prediction error. So that's shown right there. And we find that F using some function approximation algorithm. But here I want to take a different tack and ask, what is the theoretically optimal F? And to do that, we'll replace the next state of the system with the the true dynamics, the data generating model, which of course we don't know in real life, but this is a theory problem. So we'll pretend we know what it is. And that's typically a function of both the observables and the unobserved variables. And next, we'll replace the sum with an expectation over the stationary distribution for the system. And from here, we do the variational calculus, setting the first variation with respect to the delay embedding map equal to 0. And then after a bit of rearranging, we find that the optimal delay embedding map is equivalent to the original dynamical system averaged over the unobserved states, conditional on the included history. And this is true for both stochastic and deterministic systems, and really any thing that we choose to include in H. Now, since in real life we don't often know exactly what the purple F is, it might not seem like this has any direct utility, but it does actually have, I think, some useful implications, and that's what I want to tell you about next. All right. So the first useful implication is that the prediction error must, on average, decrease as we increase the available history. So the reason I care about this is that Tatkin's embedding says that the embedding dimension needs to be greater than twice the attractor dimension. But what if it isn't? What if the attractor dimension is really quite large? What do we get when we don't have, twice that number of lags? So let's say that we have I'm going to simulate something to sort of think through what this implies. So let's say that we have 1,000 species generalized Lochte-Volterra predator-prey model, but that we only observe one species. And so here are the dynamics for the whole system, and then here's the time series for species 1. Now, the conditional expectation for species 1 would look like this, right? So we take the known equation of motion and condition on the current state and whatever past states of species 1 we want. Now, because we know the current state of species 1, we can pull that out of the expectation. And so suddenly this just looks like a single species model, at least the piece on the left does. And then there's this other piece which just has the interactions with all the other species. So we could think about this as a single species model with noise of a sort, where Z is the net interaction with all the other species. And so that is not really noise in the sense that it's not random, but if we were doing this from a single species model point of view, that would be the apparent noise, right? So the question really is, what happens to the distribution of the apparent noise as we condition on more and more past values of species 1? So the conditional distribution for the noise is what we're going to show here. But right now, in the top on the right, I have the distribution for Z when I don't know anything at all about the current state of species 1. So now we're going to think about what happens to that distribution as we condition on some information from species 1. So here's the attractor for species 1. It's a bit of a mess because it's really not 3D. It's more like 8 or 9. And I've picked 3 representative points that we're going to condition on. And those are those red dots here. So they're just picked at random. And we're going to use the information there to update what we think about the distribution for the apparent noise, or for Z. Now, if we know only the current state, what we get is the distribution for Z is this red distribution, which is now strongly bimodal. And so in a sense, actually knowing just the current state is really not very good. It kind of makes things worse. As we add one lag, much of that bimodality disappears. And it's clear that the mean depends on which point we're conditioning on, because the Z isn't really noise. It's not on average 0. Now, as we go to 3, 4, and 5 lags, we can see that including more history significantly reduces the range of the possible effective noise, even in this very large, very sparsely observed system. And so this is what we get when we don't have enough lags, right? So when we don't have enough lags, we have this, bimodal distribution, but even just one more lag eliminates a lot of that. And so the upshot is that including history can significantly reduce the apparent noise, and that the significant noise reduction happens with far fewer lags than are needed to fully embed the attractor.
Mm-hmm.
All right, the second implication of this setup is that the conditional mean lets us add mechanism to our data-driven model. So let's say we know the dynamics of the observables in isolation, maybe from first principles or through some exclusion experiment. Then we can use the conditional expectation to obtain a mechanism-constrained model where the lags of the observables are just used to account for the effects of the unobserved states. Right? So F0 here is the sort of self-interaction terms, right? And then we use EDM to account for the interactions beyond that. So interactions with things that are outside of those observed variables. So as an example of this, let's say that we have a predator-prey system where we had time series just for the prey. And that's shown in the orange in the middle there. And now our standard EDM forecast for this using just lags of the orange time series would look like this, which is not bad, right? The dark gray line is our prediction. It's not terrible. Now, let's say that we had some auxiliary data on the prey growing in isolation, and the time series look like that in the middle. And we use that to fit this the blue model all the way on the left there. All right. So now if we add this as a constraint, right, and then we use our EDM and the past, conditioning our EDM on past values of the prey, right, we estimate this function g of h, right, and that's going to compensate for the predator that we're not observing. And when we use that, we get our mechanism constrained EDM, which actually does in this case, a much better job of making predictions. Now, of course, I should say that how much better depends a lot on how much data we have, right? If the orange time series were a lot longer, the EDM would work just fine, right? Adding the constraint probably wouldn't matter as much. Now, all right, the last thing is that we can use EDM to complete a mechanistic model. That is, using EDM on the residuals from a given model can let us compensate for unobserved variables or model misspecification. And as an example of that idea, here's a simulated 6-species system, again, a generalized Lotka-Volterra model. The time series from this system look like that in the upper right. And then as a potential mechanistic model, I've fit a structurally correct model to a subsets of the data using 1, 2, 3, up to 6 species worth of data to predict the future state of just species 1, right? So if I see 1 species or if I saw 2 species, up to all of the species in the system, right? And then ask, okay, well, if that's the model and that model has the right shape for the dynamics that we're fitting, how well can we do when we have a subset of the system? Well, so the prediction accuracy we get doing that is shown in red. And although there is a modest increase in accuracy as we increase the number of time series that are available or the number of species we have data for, we really only see a good prediction accuracy once we have data for the whole system. Okay, but what happens if we use EDM on the residuals of each of these models to try and improve our prediction accuracy? Well, when we do that, this is the prediction accuracy we get. And so what this tells us is that using EDM on the residuals makes a big difference in prediction accuracy. We get nearly the same prediction accuracy for all of our incompletely specified models. So to summarize, I started out by showing that memory effects are expected whenever we have a partially observed system. I then showed that for ecological time series, the EDM generally outperformed the linear model. So we need both the nonlinearity and memory. Although the biggest differences occur in systems with positive Lyapunov exponents. By incorporating information on the control parameter or putative environmental driver, we could use EDM to reconstruct bifurcation diagrams and anticipate critical transitions. And then I closed with some brand new work thinking about EDM as the conditional mean for the system dynamics. And this facilitates incorporating mechanism and completing models with EDM. And I want to close, but with this one observation, which is that if the residuals from our favorite model are predictable with EDM, that suggests
Oh,
that some important state variable is missing. And
oh,
that's
yeah.
probably good to know.
Uh-huh.
So
Wow.
lots of people have contributed to this, although I am solely responsible for any errors in the presentation. And I am, of course, grateful for funding as well. And with that, I'd be happy to take any questions.
Wow. Thanks so much. Wow. Yeah, yeah, yeah. Ooh. I think I'm very sure that there should be a bunch of questions from audiences. Yeah, please feel free to ask a question after unmute yourself.
Uh,